A very warm welcome. Good morning to everyone joining this webinar. My name is Harold Thomas from Angst+Pfister, and today we're talking about industrial MEMS for motion. And I have on my side Juhani Petari from Murata, and we give the audience a little bit time to join. And I would say in about a minute. We can start then with the presentations. Just some housekeeping things. If you have questions, you can use the chat bar. The presentation is structured that we are having in between some poll questions, so keeping it a little bit interactive. The results will be displayed to you, and later on at the final stage on the presentation, we'll also open up the lines for a Q&A session. And to answer your questions. So maybe in between there are some questions that can be answered from scratch within the presentation, but we will see how that goes. So Juhani, everything okay? Fine with you here? That's okay?
Yes.
Good.
Yeah.
Very good. All right, let's start. So my name is Harold Thomas from Angst+Pfister Sensors and Power. I'm leading this session here today. And I also would like to welcome Juhani Peltari from Murata. And maybe Juhani, you introduce yourself a little bit.
So hello everyone, Juhani Pelttari from Murata Electronics in Finland. And my role is in business development for MEMS inertial.
And then got frozen a little bit. So in between Juhani will join to the presentation. So we're a long-term partner of
in various roles, but late.
Juhani, you broke up a little bit, so sorry.
Okay, sorry.
Good.
So Juhani Pelttari from Murata and Industrial MEMS Business Development.
Excellent, good. So presentation today is I do a brief introduction because there are some interesting points behind the product development Murata does, and I'm leading the presentation towards this section. I give you a little bit of an overview, so who we are, who is Murata Finland, and some guiding lines to the MEMS findings we see with the existing products. All right. So we, as Angst+Pfister Sensors and Power, we are a long-term partner of Murata, and our history can be found in a standard distribution business. But as of today, as we have changed over the years, we also are a sensor manufacturer and a sensor solution provider. That is basically what we are offering. And we are part of Angst+Pfister Group. And Angst+Pfister is manufacturing elastomeric materials for various industries, targeting applications like material processing, heavy machine industry, but also medical and food processing. So on the right-hand side, you see the sensor and power solutions area. And what we do exactly is basically that is the common thread we have. It's merging sensing technology with elastomers to a so-called sensing element. So we integrate MEMS sensors to buffers in order to sense pressure and vibration or acceleration. So looking at these sensor elements, I pick today this example with Murata sensors that are potentially used in the environment everybody knows quite well, and that is positioning by using MEMS technology and GPS data. So the point is today, especially gyros are used more and more in those GNSS positioning systems. So because and the interesting or threat in this area is that GNSS signals can be blocked by obstruction or jammed or spoofed. That is in cities, but that is also a no GPS situation possible out in the fields when you use different things. Um, and so the important thing here is also the drift over time. That is very important. And today's solutions are focused to combine then GPS with MEMS. And why exactly the MEMS sensor from Murata is important is I will show you in a bit. So we have here a question. Just I want you to answer that briefly and say, how are your applications required to operate when GNSS signal are degraded or unavailable? Maintaining full navigation performance, limited performance, so short outages, graceful degradation is acceptable, or GNSS availability is assumed. So please vote, and we can see then later on how the result will be. So you can see that main things are just short outages, and the main part like 80% or either accepting short outages or maintaining full navigation performance. So Joni, have you seen very similar experience from the market? Probably not yet so far, because Murata really is focusing also on the active part, like degradation, dynamic inclination things. But have you seen that as well?
Yes, definitely. And of course, when full autonomy comes to these machines, then more and more
Mm.
kind of full navigation performance needs to be achieved, even with GNSS outages. So maybe
Mm.
typically nowadays we stop the vehicle if GNSS is completely lost. So inertial sensors are kind of complementing GNSS still, and maybe not like taking over in industrial space for full outages, but it's coming.
Yeah, yeah. It's interesting because that brings us directly to the next slide, which is basically the level of the IMU performance. So for signal outages, most of the known errors of for velocity or position are becoming relevant after a time of around about 10 seconds, and will be of a linear behavior. So here's basically an example you can see from different IMUs measured at with low, and mid, and high grade specification. So after, as an example, after 20 seconds, a low grade has about 0.2 meters per second error, while the mid or high grade are between 0.04 and 0.06. So that's the difference we also do see in most of the applications, and that is basically also why we that's matching with the specifications or say the very general classifications of IMUs, and that's basically why we picked the Murata gyro as an example. That is a product that has, it's basically a consumer classification product, price product with very close technical performance level, and that is interesting for various of the applications. And in that sense, we also see levels of sensors that are specified with either positioning or dynamic inclination. So that on the left-hand side, you see the gyro or accelerometer specifications. On right-hand side, you see the series of products Murata will be launching over the next months and years. And the interesting part is that the Murata sensor, the SEH16T, is having a very good performance. So for testing, you already need a zero point 0 degree per hour ring laser gyro, that which is priced around 50K 50k euro in order to achieve a good reference. So when using such accelerator or you're combining this with a good algorithm, you will achieve a high performance great sensor unit. So whether it's for machine control guidance or dynamic inclination or robotic control. So that is basically an interesting thing what we have seen. So I have a next question for you that basically is asking what the biggest challenge is when you integrate inertial sensors into your system. Is it achieving the required accuracy, robustness to blockages, sensor fusion complexity, or cost at deployment scale? So result almost what I had is at least expected. Maybe Juhani, you've seen probably the same thing. So achieving required accuracy is most of the important things for this kind of application. Sensor fusion complexity is way less than the target for the required accuracy. I think we're not talking about a centimeter grade or pinpoint, but at least a high level of accuracy. Sim, what do you expected or?
Well, yeah, and I think the first two are kind of tied together in the sense
Mm,
that in order to achieve the required accuracy, you need, let's say, in many cases, especially in dynamic applications, you need very sophisticated sensor fusion. So if
yeah,
that and that can be difficult, but of course more and more stuff is available on the market. But
yeah,
I think accuracy is something that Murata sensors are very good for. So it's a very good starting point to look at
yeah,
Murata inertial sensors.
yeah. That's good because that brings us to the things we've found so far with the experience of the even the first generation of gyro products. So what are the findings we have seen so far in these sensor areas? So it's a little bit smaller picture, but I'm trying to explain that. So regarding sensor noise, what you see is that the red line is basically a high-end IMU level. We put a inclination sensor to it. That's a SEL 3400 that levels on the same performance, and the blue line, the wider blue line, that is basically the first generation of Murata's sixth of sensors. With the new generation like SEH16, that improves by a factor of 2. So that is one of the important things. So the acceleration part of this product makes it very interesting. And combining that or doing things like recalibrating dynamics, that basically is when you have by filtering in place and trying to achieve a dynamic inclination system. So that's what we have seen, and I try to find also a picture of the plot we've done in the lab with the measurement. So we put a SEH16 on a platform and measure over time for a few hours, basically during the night. And the interesting thing is basically that we have seen a so-called tidal effect of the moon during the time of the measurement. So even when it was very, very little, and you have seen it only in the noise band, it was seeable. That is basically there's this high and low tide function we can see in the ocean. That is basically what we have seen in this sensor as well. So the effect of the moon basically had an impact on the measurement. So uh, what the outcome of that basically is, that we see that there is a discussion starting, that it's very provocant question, but do we do we can we live without a GPS and navigate or position our systems without GPS? Today we see it's a combination, but if you have such systems in a no GPS area, and it's a calibrated sensor, then basically it helps to achieve a way better position with that kind of sensor. So the we can measure the Earth rotation and the position on the Earth, and that basically brings us to the next generation of products. So I'm saying it's not today that we can solve that thing, but it's also an North Seeker system that basically is rotating, that already achieves the sensors. So and that's basically why I want to hand over to Juhani, and we are going to switch presentation for his part, and I think that is the last slide. Yeah, and then I would like to thank you for participating, and now hand over to Juhani. Thank you.
All right, thank you. So continuing on that side and MEMS inertial sensors, there's a few words about Murata. So many of you may know Murata is a big Japanese company focused on electronics, and of course well known for our passives and then also wireless products and battery products. But what I concentrate on is inertial sensors, and that's then Murata Finland. So when I joined the company, we used to be a company called VTI Technologies, but it was acquired by Murata already in 2012. So it's been long history now, full part of Murata, and yeah, we are around 800 people in Vantaa, Finland. That's basically the airport of Helsinki, capital of Finland, is in Vantaa, and we're pretty close by it. So we have our own MEMS fab there, and it's focused on manufacturing inertial sensors. So in practice, that's then accelerometers and gyroscopes for various use cases. In MEMS, which is micro electromechanical systems, everybody still has pretty much their own kind of technology. There are some, let's say, consumer products that are already now like pin to pin and might be replaceable, but typically these sensors are quite unique. And when you design in one of these, you are pretty much sticking to it because of the parameters and having everything very much proprietary to that sensor. And what is unique for Murata sensors is definitely the accuracy, stability, and reliability. So our sensors are not the ones you find in cellular handsets, but rather the ones that are made for critical and safety critical applications, such as automotive areas. Biggest portion of our sales is going into mobility, and that's then passenger vehicles. And the biggest application there today still is vehicle dynamics, so electronic stability control of a car, where linear acceleration is measured and angular rate is measured with our sensors to keep the car on the road. So basically comparing what the car is actually doing to what the driver is doing with the steering wheel, and then the braking system is making up for that. And then of course we have multiple other automotive applications, but the biggest portion of our growth now, and which will be the biggest application area for automotive, is this autonomous driving and advanced driver assistance systems. So nowadays already the robotaxis are very much driving with Murata sensors. So we are very much present in those. Of course, the volumes are still very small compared to regular passenger vehicles, but that industry is growing and starting to be visible. In the middle row, you see industrial, and that's basically the focus of my work, is looking after applications that are non-automotive, but of course, a lot of them are similar. And today we are maybe more focused on this first bullet in machine control and some touching on these instrumentation applications as well. But of course, applications where the environment is very similar to automotive, we are also strong there with our technology. And they are, of course, new interesting applications coming in the future for drones and humanoid robotics and satellites and so on, where inertial sensors can be applied. We also have a business area in medical, which is then kind of a niche area, but it's an interesting one where we supply typically these kind of pair sensing elements. And our MEMS sensors have very high capacitance, so they can be utilized in those applications where long battery lifetime is needed. So we are supplying almost all the Western pacemaker manufacturers with our sensing elements. They make their own electronics, and then it's kind of an activity monitor in the heart. So basically, when you go out jogging, you will bring up the pulse of the heart, and then when you lie to sleep, you will uh, go down with the pacemaker pulse, so that it's more convenient for the user. We also have some patient monitoring, kind of remote patient monitoring, in the sense that it's not the sensor can be attached to the bed, and we can still see the signals of the heart. So when your heart is pumping, it's displacing blood, which is displacing your body, which is then displacing the bed, and eventually with a very sensitive sensor, you can also see this and utilize the signals there. But like I said, the middle row is most of the focus today in terms of this industrial and machine control applications. Um, and well, it's true for all segments, but of course, especially for industrial, the high performance is something that customers are seeking. So whether it's rotating laser levels or grade control systems for different kind of construction machines or structural health monitoring systems, it's always about achieving very high accuracy. And that's where Murata sensors are very good. So we have very good stability over lifetime and temperature, and then we have sensors that can tolerate very difficult environments. And yeah, there's a number there in the low bottom. So what this kind of MEMS inclinometer, it's essentially an inclinometer is an accelerometer just using the gravity to measure the tilting angle against the gravity vector. So with our inclinometers, you can detect tilting changes of a 1,000 of a degree, so very, very small. That's not, of course, the actual accuracy over lifetime in the application. So that might be then closer to something like 0.1 or 0.05 degrees per uh, in tilt, but this is the resolution you can achieve in short-term measurements. Yeah, in machine control, especially this inertial sensors are becoming standard. So there was, of course, already great control systems in like 10 years ago, but those were quite expensive aftermarket system. But now, if you buy a new excavator from almost any major manufacturer, they will have this kind of great control systems embedded to the systems directly from the factory. So it's factory installed systems. Same thing with agriculture equipment. Tractors are starting to drive by themselves almost everywhere where the fields are a little bit larger than very small. And our sensors are very good for this. And then, of course, full autonomy is the thing that's coming and will create more space for this. Uh, if I talk about IMU, it's basically inertial measurement unit, which is then a similar thing as a 6 degree of freedom unit, so 6 DOF, and that's a 3-axis accelerometer and a 3-axis gyro combined. So an IMU combines this 6 degree of freedom sensor and then some mathematics in an algorithm typically to measure something. I think there was a poll question here.
So there's a poll question for you, gentlemen, to the audience. What is the property of a MEMS sensor that is very important for its application? Is it robustness to vibration shock? Is it stability over lifetime? Error due to geographical location, basically that refers to calibration and simplified use of modes available in the ASIC or even filters. So if you please give an answer to that, we will be happy. So stability over lifetime, Johanni.
Well, that's
and
yeah,
and
like I said,
robustness
that's also
to
the strong
vibration
point
shock.
for us.
Yep. Yeah, maybe a good question for you. And
Yeah.
robustness to vibration and shock. Basically, what we have seen is that in various applications, seen some kind of piezo material, but that if that is overloaded, it gets blinded and is basically not operating for a few moments and then is coming back. So that is basically um, what I interpret into robustness to vibration and shock. And you have that specification in the data sheets as well, right?
Yes, certainly. And yeah, our sensors are well. There are of course many unique features in the MEMS how to make this robustness against shocks and vibrations. We will
Mm.
not go into the details of those, but this is also where we excel. So the for a long time, the biggest application for us has been this electronic stability in the car, and especially when it has been integrated to the brake controller of the car, it's a very hostile environment. So we've spent years and years of developing to make our MEMS very suitable for this kind of tough vibrating environments.
That is reflecting also to the heavy machinery market because
Yes,
vibration is there day in, day out, right?
yes, yes. It's very similar, and that's why also we are very successful in these markets. So,
Good. Okay. Good.
all right.
Go ahead.
So we touching a little bit more on machine controller. I will have two, let's say, application examples of how the system actually works and how the inertial sensors are used in it. I will have one for excavators and one for tractors, and but of course also material handling equipment and all kinds of autonomous machinery are very much target applications for our sensors. But showing how, for instance, this agricultural auto steering has been there for quite a long time now, and we are very strong also in this application. So the idea of the application is that the tractor is driving by itself. Typically there is still the driver is in the cabin, but it's more like monitoring and then controlling the other applications that are in the tractor when you are doing different kind of work. But the GNSS is the focus of the application. So it has high precision GNSS, and but then that needs to be combined with IMUs, both for, let's say, very short term outages, or the fact that GNSS data is not, the refresh rate of the GNSS is not very high. So you need inertial sensors to combine with GNSS. But also in terms of this kind of machinery, when it's not driving on the road and you want centimeter level accuracy, as is visible in the picture on the left, you can see that the terrain effect is very high in these. So when the tractor is tilted, the GNSS will give you the location of the antenna, but it doesn't tell you how the tractor is oriented. So that is done with high precision inertial sensors. So we have accelerometers and gyros integrated into the receiver, and then it knows the orientation all the time, and that can compensate so that you can still have centimeter level accuracy when driving on the field, even though the terrain is tilting the tractor all over the place. Kind of similar, but a little bit let's say even bigger use case today is this grade control system. So nowadays the the excavators, when digging on larger construction sites, they typically utilize this kind of grade control system, and it's first of all, of course, to make it more efficient and easier for the operator. But of course also can be applied so that you don't make mistakes. So you don't dig too much there and you don't dig too little there. So traditionally, of course, you would have a guy come there with the measurement pole and measure, and then you do some digging, and then again somebody comes there with a measurement pole and you see where you're at with your digging. But nowadays you use this grade control system, and you have the blueprints in the cloud, and the excavator basically knows how you need to dig the whatever kind of surface you are creating. And how that works in practice is that in the smaller picture on the right, you can see there will be dual GNSS antennas on the back of the machine, well, typically on the back of the machine. And that's used for, again, high precision positioning of the antennas. But then when you have two antennas, you also get the heading of the excavator. And now you know perfectly the position again of the antennas and well, perfectly, but let's say with high accuracy. And then also you know the heading of the system. But you need inertial sensors in the base of the machine. So in the larger picture, you can see on the base of the machine in the cabin, you will have one inertial sensor to tell you how the excavator cabin is oriented. And then you need another one in the boom of the machine, and then also in the stick of the machine. And in let's say 50% of the cases, you have an IMU also close to the scoop, so that you get the final linkage. There are some other sensing technologies also used sometimes for the scoop, because that's, let's say, the toughest environment for any inertial sensor. But yeah, Murata sensors are the ones that might survive in even in that application area. But then once you have all of these IMUs and you know all of their orientations, you basically know where the tip of the scoop is compared to the GNSS antennas, and that's when, yeah, you can create a blueprint, and the excavator will dig accordingly. And you can also dig underwater. You can make some limitations that you don't go too high above. You don't break anything if you're digging in constrained spaces or something like that. So the excavator grade control system typically has at least 3 IMUs, maybe up to four IMUs attached to the machine, and then GNSS. Just touching on other application areas is also this kind of construction tools and systems. So, well, traditionally rotating laser levels and digital bubble levels, these are kind of static applications. So you put the instrument there and then you measure. And when you're in static condition, then of course an accelerometer or an inclinometer is enough for that measurement. But once you install also movement, then you need to compensate. You cannot distinguish between linear acceleration and tilting, and that's where you also need gyroscopes. So nowadays, this kind of survey poles and surveying instruments, typically you don't want to stop and be full static, but rather you have inertial sensors to compensate. So the survey pole, you can move around with it and you can just touch places. And even though your antenna is in the other end of the pole and then the tip, you can compensate the orientation of the pole with these inertial sensors. So typically you have a 6 degree of freedom application also there. A little bit was touched already in the first presentation, but basically the sensors we offer is accelerometers and, like said, inclinometers, which is just optimized for tilt sensing, and then combo sensors where we have angular rate sensors, so gyroscopes, in addition to the accelerometers. And I mentioned that we do offer in the medical field some of these the bare sensing elements for pacemakers, and then we have these ballistocardiographic solutions also for this kind of monitoring the heart from the bed or from a chair or something like that. But the highlight of today and maybe the portfolio right now is definitely this new SCH16T Murata MEMS sensor, which is a 6 degree of freedom product and integrates very, very high accuracy for any kind of sensing. So this is the product to look at in various applications. It's a pre-molded packaged sensor with a 24-pin layout. It's a solderable component, 3.3 volt, and there's plenty of stuff built in for functional safety in this product because it's the sister product of this series is also going to high volume automotive safety critical systems. So basically all Murata sensors are qualified against AEC Q100 automotive standards, and then functional safety is also built into a lot of them, so they are very good. Typically we specify the functional safety for the automotive product variants, but these sister products that we have for industrial space, they of course feature the same kind of capability also. In this product series, there are actually now already 4 product variants. So these are like columns here. So you can see we have the, let's say the standard product variant is this SCH16K01. That's a sensor that's usable for most applications. It's very, very high accuracy, very low noise gyro, and also offers capability for almost all kind of machine control applications. But then we have, let's say, different applications where there might be benefits for a little bit different variants. So like the next one is SCH16TK10, and that's what we call kind of the drone version of the product. So it's definitely a product that's offering also the stability that the K01, but it offers more dynamic range. So it gives you up to 2000 degrees per second measurement range for the gyro, which basically is something that can be visible in drone or other very high dynamic applications. Typically, applications like excavators or tractors, they don't move that fast. So you get more benefit from utilizing the standard product or other product variants. But in high dynamic cases, we offer this this product version for that. And then we have SCH16TK20, and that's a product variant which is for highest accuracy applications. So actually the accelerometer inside is different, and this one is an accelerometer that features extremely high stability over lifetime and temperature. So if your application is something that you don't think that it might even be possible with MEMS, then this is something to look at as a possible use case. And then finally, it's not actually even out there yet, but I'm showing it here. So it's the H16DK30. That's a product we plan to launch in the end of the year. And that's for, well, it says high dynamics here, but it's especially for those high vibration, high shock environments. So the accelerometer inside this product has features that makes it very insensitive for shocks and vibrations. So it can offer extremely nice performance in very difficult environments. It can be construction machines, but anything where you can see that you need to tolerate very difficult stuff. I think we have another
Juhani,
poll. Yeah.
yeah, but Juhani, is that there's one question that how you can explain that difference on the accelerometer? Is it like it sounds like a damping?
Yes. So what is kind of very unique and but common to all Murata accelerometers is that in an accelerometer you have a cavity where there is a moving mass inside, and we control the pressure inside that cavity. Where there's inert gas inside the cavity, and the pressure of the gas that's inside the cavity will kind of make a mechanical low pass filter to the sensing element. And in this K30 variant, the the gas pressure is much higher and the spring thickness is higher, and that's where it basically makes it that it has a mechanical low pass filter in the product. It will kind of filter out mechanical noise already in the mechanical environment, and not just
Mhm.
filtering afterwards in electronics.
So it's a built-in.
It's a built-in
In,
feature, but it's in all Murata accelerometers, but in this K30, we utilize basically a sensing element that's also used in electronic stability control in the brake controller environment.
Mhm. Good. And there's a poll question coming up in the next slide. Let's see if can you use that. No, this is seems not popping up here.
I think now maybe it's, well,
Just ask Merve if she can help to bring up the poll. But basically, the poll. Okay, if it's not popping up, I'm asking that question. So, what kind of MEM sensors you would like would make your job easier? Maybe you can comment then on the chat field as well, so that we at least get an answer to that. So, is it just a sensor only with high output data rate? Is it a calibrated sensor? I assume it's a factory calibration with digital interface. Is it a sensor with an integrated processing unit? Um, for self configuration, or is it into a sensor with processor and application based algorithm? That question leads more towards the product developments over the next coming years. So Juhani, basically what we are seeing here is sensors with a certain output data rate. I think it's about 2 kilohertz max. When running a filter on it, on with a processing unit, I think that goes to an output of 80 to 100 hertz. And the question to integrate, I think I'm adding here. Okay, Maver says it's up here, but I don't see. Um, okay, sorry, that's my mistake. So calibrated sensor with digital interface is very interesting. Sensor with processor and application-based algorithms. So um, sensor with powerful processor for self-configuration. Nobody voted. So, Johnny, what do you think? It's calibrated sensors with digital interface, and it's a sensor with a processor and application-based algorithm. I think the K30 goes already in that kind of direction, but not having a processing unit. It's just a pure sensor with some integrated ASIC, right?
yeah, I think most of the current portfolio and what I'm showing here in the products, those are kind of in the first category. So we are actually doing very extensive calibration for our sensors, and they all feature the digital interface, and that's the natural one. But the second one that's also getting votes, that's an application area we are studying, and yeah, maybe later on there might be some news on that front as well. So it's I think it's very much in line what our
Mm,
offering is now and hopefully will be in the future. And definitely this high output data rate part is also all of these products feature quite high output data rate. So they are used in autonomous driving kind of applications also, where it's very essential to have the
Mm.
all the latencies under control, and also the data synchronization is a pretty key feature.
Because that leads to some questions that have been raised already. I think it's worth to just bring that up here. Does Murata plan to integrate kind of AI into MEMS sensors in the edge? Basically, that means you need processing power.
Yeah, like I said, we are looking into that, and maybe more details on that following. But yeah, that's something we're definitely looking into. And of course, AI is plenty of used already in our production and in the sensor development. But when it
Hmm.
goes directly onto the component, it might still be some time. But it's something that's definitely looked at.
Okay. Well, I've seen that basically is, I think, the last part of your presentation. Am I right?
I
I
think
think
there's
so.
a couple of more
Okay.
slides, but just
But just,
easy.
yeah, just stay with the sensor, because there are some questions to the sensor units, for example.
Yeah.
You've shown the SEH16 with a height of 2.9 millimeter. The inclination products like the SEL 3300, 3400 are in a overmolded package. Are you planning some low profile products similar to the SEH, or even with lower profile?
Yes,
Because you
there is.
mentioned also the BCG, that basically, but that's a pure die business, so it's not an unpackaged version.
Yeah. So you can see here basically the packages we offer for our components in the current portfolio. So these combo sensors are definitely becoming thinner, and in the accelerometers, this is still, it's actually, yeah, comparing these, this is not as big as it seems on the picture, but it is still, there is some height to this sensor. It's a very good accelerometer package in terms of stability for over time and temperature. So that's why we also use it for, because MEMS is a mechanical sensor, and the package is a key part of being a high accuracy mechanical sensor. But I can say that there is also development towards next generation accelerometer products, and of course, well, all of these components are shrinking still. So the height is something that will come eventually when we have news on next generation platforms for accelerometers. But should be noted that even these products, they are not that big, and the advantage these packages can give is the stability over both time and temperature.
At the BCG, that picture, that is not a sensor, it's a processing unit, right?
Yeah, so
Right side.
for this ballistocardiographic solution, we offer a pre-programmed microcontroller and the sensor, and
Okay.
this microcontroller features that. But of course, in the future, it might be that these will also be integrated. But
Mm. Mm.
that's the current portfolio you can buy if you're interested in the
Yeah.
BCG.
Okay. So next question is, what is the dynamic range of the 16T in frequency, so bandwidth?
Uh, Off the top of my heart, it little bit varies also on the product variant we see. So but the bandwidth of our sensors is typically in the, let's say, hundreds of hertz. We are not
Mm.
in most cases in the kilohertz or tens of kilohertz range. We even used to have products that had bandwidth of only like tens of hertz. But nowadays, even the K30, which has the high damped accelerometer, it will still be more than 100 hertz. But it's not several hundred hertz, whereas these will be several hundred hertz for the accelerometer. And for the gyros, there's a little bit more bandwidth. But like I said, it's still kind of low bandwidth sensing, in the sense that the high frequency range is something that we try to filter out from the customer, because it's essentially not the information you want to see if you're in machine control or something like that.
Okay, that leads to the next question, is like how you can improve to a higher output, but keeping accuracy.
Basically, we the then we could consider that that might be relevant for this version. So this is the bigger range in terms of gyroscope for the drone applications. But the noise density is something that we actually, our noise density of the gyro is so good that if we would just leave it as it is and calibrate to a wider range, we run into export control regulations. We cannot sell. There is a there's a limit that's 500 degrees per second for the gyro noise. Uh, and if we just calibrate as it is, it would be a dual use item, which is then highly controlled and not available to sell off the shelf. So that's why the noise is worse in this product. So it's intentionally, we need to artificially make it worse in terms of noise. The product itself actually is better than this. But then, of course, it depends what dynamics you're talking about. But in practice for gyros, we don't have that much drawback anymore from even adding the range.
Okay. Next question is an interesting one. Well, basically, it's the same we had before. Is that Murata offers so-called telecom modules certified. Is Murata going to offer a module? I think that is related to a sensor plus processing power, because Murata is known as a company that does high level integration and can make complete modules on a different cost scale than individual smaller businesses can do. So is there an intention to offer such kind of modules?
Well, the intention is probably to stay on component level, but if we consider modules as components like integrating a microcontroller with the sensor, like I said, it's something that we are definitely looking into, and most likely we will have more news to you by the end of the year.
Okay. Yes. I'm checking just the questions. So if there are some more questions, just send them. Um, let's see. Interesting. Okay, that's more the concept of how companies are working. Why do product data from various manufacturers of those sensors do differ so much? um, but I think what I've seen is it's different explanations or wordings used for specifications. So sometimes it's millimeter per square second. Sometimes it's milli-G. Sometimes it's a various way in relate to temperatures. I've seen that let's say the high damping unit runs to 85 degrees C, for example. I think that's related to these things here. Whether you specify how you specify the measurement and the operating range, right?
Yes, and like said, MEMS is still very much an industry where sensors differ, and it's not very easy to find pin to pin, and in the specifications there's plenty of specsmanship behind them as well. So Murata is actually typically a quite conservative when it comes to specifications. So we our typical is 3 sigma limits for industrial sensors. For automotive sensors, it might be that we specify like 9 sigma limits for the sensors, and then those are guaranteed. But yeah, that's difficult for customers to compare the specs because everybody does their own thing, and sometimes somebody makes typical spec with only 1 sigma, and it's not apples to apples. So yeah, you need to spend some time to analyze this. So then ask from support from Angst+Pfister and us, because we will gladly help you in in comparing specifications if you're not
Yeah.
sure how it should be done.
Okay, there's the next question. What kind of filters you do integrate into the sensors? I think basically it's more to the ASIC. So maybe some pre-installed fundamental things.
Yeah, in the current products, the filters that are, it's basically they are
Low pass.
low pass filtering for available, and you can select different bandwidths per your need and application requirement. And like I said, for the accelerometers, there's also this mechanical filtering due to the gas damping, the over damping of the sensing element. But other filters we don't integrate yet. So of course, in the future there might be algorithms like Kalman filters or whatever, but then that would be something that requires more processing capability than the current component selection.
Mm. Okay. One question: can you go more into detail on how the calibration process of the sensors are working?
So yeah, basically in our production, all the components are calibrated over temperature, and we have like plenty of factory space reserved for very big machines that are basically ovens where we have rotations capable, well, kind of rotational rate tables inside the ovens where we can do high accuracy calibration. And typically, what's done is measurements at room temperature, at hot temperature and cold temperature, and then those results are used for the built-in calibration parameters inside the sensor. So they would be like third or fourth order compensation for temperature dependency in the sensors, a little bit depending on which sensor series you look at. But yeah, we calibrate a lot.
So that basically then refers also to the idea of the positioning. So the products are calibrated at Murata, Finland. You know the geolocation, and from there, basically if you go south or north, you have a defined error in degrees, and that basically you can make use of in your or in the working environment. Let's say is
Yeah,
if you
basic.
go 500 kilometers south, you have an error of 2.5 degrees, but it's a known error because it's related to the calibration and the
Yeah,
position
it,
on
it
the earth. Right.
if it of course depends on the application what is needed, but we do also offer the reference what is the gravity in Helsinki where we calibrate our sensors. So of course, if you're seeking for that, let's say 0.001 degree accuracy, then you need to also look at the effect of sensitivity because the scale factor calibrated in Helsinki will not be exactly the same as in Brisbane, Australia. You will need to consider that parameter in, but it's
Yeah.
very let's say not very frequent applications that need that high level of precision. Then Earth rotation for the gyros is something that's of course visible, but we take that into account in our calibration already. So we know which way the Earth is rotating, so we can take care of that.
Okay. Good. So I think we are fine with all the questions. If you have more questions, then thank you very much for your time. If you have
Thank
more
you.
questions, just send it to us here in the chat box. We leave that for a while open. Or you send the emails to other chances to meet us at Sensor and Test during next week in Nuremberg. We can talk there on maybe deeper informations and product details. And just one comment on the product availability. K1 and K10, they are available. You have shown a slide that shows the MEMS eval board plus some PCBs where the sensors are attached to. There are the K20 is basically approaching
Yes.
We have orders in place, so that will be heading to us during the next weeks. And K30, you said it's basically a release towards the end of year, and what I expect is something like electronica in November timeframe is more concrete and more precise information available about start of
Yes.
production. Okay, very good. So we're at the end of the show. Johanni Mary, thanks for being our guest here presenting. Thanks to the audience. Appreciate that you have joined this session here, and hope to hear from you. And we'll be following up with several questions later on. Thank you very much, and have a great day.
Thank you. You have a
Yeah.
great one.